Okay, so what we're going to talk about first are mutually exclusive events, and we're in our workbook on page 455. So it states that two events are mutually exclusive events if the events cannot both occur in the same trial of an experiment. For example, when you toss a coin, the coin landing heads up and the coin landing tails up are mutually exclusive. Because when I toss a coin, can that happen at the same time? No, it's going to be either heads or tails. Yes, sir.
Number one, what page is this?
We're in our workbook, page 455.
And are you recording today?
Yes.
She's good now.
Okay. So if you look on page 455, let me scoot back a little bit, and we'll just take a look at this real quick. They give us an example. It says a dodecahedral number cube has 12 sides, numbered 1 through 12. What is the probability that you roll a cube with a result that is an even number or a 7? Okay, so are these events mutually exclusive? Can we roll an even number and a 7 at the same time? No, so they are mutually exclusive. So what we would do is we would find the probability. We would just add those probabilities. So to find the probability of one or the other, we would just add the individual probabilities. So how many even numbers are there? 1 through, okay, so this would be 6. And how many 7s are there? 1. So it would be 7, and it's 7 out of 12. So when we see this, what is the probability that we roll and the result is an even number or a 7? There is no overlap. Our even numbers are 2, 4, 6, 8, 10, and 12. And there's only one 7. So there is absolutely no overlap. They cannot happen at the same time. Okay? Now, oops. I lost my one I wanted. There we go. So, if they are mutually exclusive, all we do is when we're trying to find the probability of one event or another happening, we just add those individual probabilities. Make sense? And you know what? We really did this the first day, didn't we? We were just counting up and looking at our sample space, but we really did. We found the probability of this, and we added to it the probability of that. But when we do have overlapping events, where they have one or more events in common, we're going to have something in this overlap. And when we have something in this overlap, are they mutually exclusive?
No.
No. And it changes how we calculate the probability. So, what we do is we find the probability of A plus the probability of B. Then what happens is this part in the overlap, if we do all of A plus all of B, haven't we counted that overlap twice? We have. So what you have to do is you have to subtract out the probability of this intersection of our overlap.
What are we finding?
So when we have events that can occur at the same time that are not mutually exclusive, okay, so let's go back to that cube, that number cube. What if I said the probability of rolling an even number or a number less than 4? So an even number, we'd still have 2, but this time the 2 is even, and it's also a number less than 4, isn't it? So we have something in that overlap. We'll still have 4, we'll still have 6, we'll still have 8, we'll still have 10, we'll still have 12 here, but we have this overlap. And then number less than 4 would be 1, 2, and 3. So we would have to subtract out that overlap because it's counted twice if we just do the probability of A plus the probability of B. Does that make sense? Okay? So, let's start by going to page 458, and we're just going to work through some of these problems because I think we've done enough with probability that these will make sense without going through every single page of our workbook. Okay. So is everybody on page 458 now? All right, it says a survey of 1,108 employees at a software company finds that 621 employees take the bus to work and 445 employees take the train to work. Some of the employees take both a bus and a train, and 312 employees take only a train. To the nearest percent, what is the probability that a random chosen employee takes the bus or a train to work? Okay, so we need to, I'm going to start by making a Venn diagram for this. That way I can visualize what's going on. Okay, my baby is being really slow in how it's reacting. Okay. In this universal set, how many employees do I have?
1,000.
Okay, so in here we have 1,108 total. Okay, it says 621 employees take the bus. So I'm going to let this be the bus and this be the train. So I know there's a total of 621 employees that take the bus. 621. And then the train, I've got
445.
445. But then it tells me that 312 employees only take the train. So in this part of the Venn that's just the train, I know I've got 312, right? Okay, so if there's 445 total and 312 just take the train, how many would have to be in this overlap?
$133.
133.
It says,
Okay, so if I have 133 here, what would be here for just the bus?
488.
488.
Subtract the little.
Okay, so if we wanted to find the probability that we took the bus or the train, are they mutually exclusive? No, because there is overlap. When they can happen at the same time. In the same trial, one person can take the bus and the train. We're done. So we would find the probability that they take the bus plus the probability that they take the train minus the probability that they do the bus and the train. So how many people total took the bus? 621. How many people total took the train?
445.
445. Minus how many did both? 133. And that gives us 933 out of the 1108.
Wow, that was quick.
That was quick.
There you